But again, others have said it, but thank you very much for coming out. Nice to get a warm reception on an otherwise chilly evening. So tonight I want to talk about earthquakes, the state of earthquake readiness in Alaska, and things that are on our plate at the community and state level right now surrounding earthquakes. So if you're interested, the picture that's on the screen here, that's actually the Richardson Highway. We found this, I hadn't seen this figure until, this photograph until a couple of months ago. This was taken in 1937 following the earthquake in Salcha. That was probably the most significant local earthquake in in historic times, at least. And I've liked this figure ever since, of this photograph with the child down in the crack. Don't do that at home. I don't recommend it, but it does give you some sense of scale, I guess. So we're coming off kind of an interesting year for earthquakes. 2014 had a lot of not damaging, not critical types of earthquakes, but a lot of intriguing ones. This is a figure. There are all the little teeny tiny gray dots on this figure are earthquakes in 2014 that we're aware of. As you all certainly understand, there are big earthquakes and then lots and lots and lots of little ones. Many of these would constitute those little ones, but you might have caught in the news that we surpassed a record at the Earthquake Center, locating 40,000 this past year, which we were fairly keen on. I'm going to single out a few during the course of this talk, and we'll come back and hit them as examples in a few different places. So I want to take just a moment and step through just a quick recap, how about, highlights, if you will, of 2014, a couple of things that are on our minds. So a couple of these earthquakes. Anybody feel the earthquake in Southeast? Anybody happen to be in Southeast back in July for the Palma Bay earthquake? I didn't feel it. I don't expect too many folks in this audience. Widely felt in Juneau. It was the biggest shaking, or the strongest shaking in Juneau in at least a decade or so. So a very significant earthquake there. We're going to zoom in just a little bit. The earthquake occurred, if you start in Juneau and you go outboard to the Fairweather Fault, right along, really at the coast, that's where the earthquake occurred. And we're going to zoom in the next figure to this area right in here. It's kind of a blow up. And one of the things that made this earthquake significant, though its impacts on Juneau and surrounding communities was fairly modest as far as infrastructure, it did take out a telecommunications fiber that was on the seafloor, one of the primary communication links into Juneau. And it's a good little reminder of the connectedness with which we live these days. I forget exactly, 4 o'clock in the morning or so, a good chunk of Southeast lost telephone communications, lost internet, all those weird connected things we don't think about or we take for granted these days. You know, the ability to use credit cards because you need to check data, verify data, things like this. A lot of folks lost all that for some time, till repairs were made and some alternative arrangements were made. But it was a good little reminder of some of the different kinds of vulnerabilities we don't necessarily think about when we're talking about earthquakes. The next earthquake we refer to as the Squentna earthquake. Rattled Anchorage fairly well and was felt some here in Fairbanks, I believe. Anyone feel that earthquake? All right, we got some hands up. I didn't. I wasn't in town. But it was felt pretty broadly. Magnitude 6.3, that too was the strongest shaking, in this case in Anchorage, in a decade or more. So another significant earthquake as far as at least being able to perceive it. A lot of photos circulated after that earthquake. There were no major infrastructure challenges or significant damage that I'm aware of, but lots of rattled homes and offices, shelves falling over, things of this nature. But but for the most part, damage was limited to things that individuals can address or deal with. I'm not going to talk plate tectonics tonight. Many of the other venues at this, or talks in this venue, you might hear a lot about that, and you guys turned out on a cold night on a Tuesday, I think you're I'm guessing you're kind of a scientifically literate subset of Fairbanks. So thank you. But I'm not going to talk a lot about plate tectonics other than to recap the basics that I suspect many people know, which is most earthquakes in this state can be traced back in some way to what we refer to as subduction, or the process by which the Pacific tectonic plate is being forced down underneath Alaska. This very simple cartoon drawing, ridiculously simple cartoon drawing, really captures, in some sense, a lot of the reasons we have earthquakes. The Squentna earthquake was interesting because it actually occurred very far, let's call it inboard of Anchorage. If we put Anchorage kind of up here, it was actually down here kind of deep. And not unexpected in any way, but not usually the earthquake we're thinking about. When we're worried about significant damage in South Central, this isn't usually the earthquake we think about. So that was an interesting tidbit from it. Rat Islands, magnitude 7.9 in June. Anybody here felt that? I'm going to guess there are more people in this room right now than felt that earthquake in total. I can't verify that, but that's my sort of back of the envelope calculation. And yet, this was the second biggest earthquake in the world last year. This is a huge, huge earthquake. This is, in order to get this earthquake from the Squentna one, the earthquake we just looked at, it would take 250 of those, all occurring at the same time right here, to equal, or to create this earthquake. Huge. When you have a big earthquake in the Aleutians, one of the primary concerns is the tsunami hazard generated by the earthquake. And there was a perceptible tsunami from this earthquake. It was recorded in many places across the Pacific. However, there was no appreciable tsunami threat or damage from it because it was very small motion. The reason, like the previous earthquake, it too occurred quite deep in the earth. And so it wasn't moving land. The seafloor itself wasn't shifting up and down in ways that generate very large waves. So we evaded that one successfully as well. Lastly, the earthquake series in Minto. Anybody feel that one? Yeah, we're in Fairbanks, so of course, lots of folks. And if you missed the first one over Labor Day weekend, you might caught one of the follow-up ones a couple of months later in October. Much smaller, I'm going to point out, than the other earthquakes we're talking about here. It would take 10,000 of these to make that Rat Islands earthquake. Think about that for a minute. 10,000 of that earthquake happening at once. It's not in Fairbanks. It's about 40 miles northwest of here in the Minto region. Again, we have the sequence of a few of the larger felt earthquakes, but there were large numbers of aftershocks, and we're able to record them well in this area. So here's a figure I want to share with you. Take a moment to get your head around this. This is the last 5 months of data. These are the number of earthquakes out in this region, in the Minto region, as a function of time. So total, up through the end of the year, we had just shy of 2,500 detectable earthquakes out there. Now, I want you to look at August. So this would be what we consider a background rate of earthquakes here. There were maybe 30, 40 earthquakes in the span of a month. After the earthquake of Labor Day weekend and all the aftershocks, in the first 2 months there were 1,500 or so earthquakes. You can see that rate kind of dying off. See how it starts to flatten out there? And had nothing else happened, eventually we would expect it to kind of go back to background rate. But then we had those other two zingers in October, and that rate of earthquakes shot back up and again began to level off. I will tell you, we've been watching this tail because it hasn't really flattened out yet. And I don't think anyone would be surprised if there was follow-on activity out there. To us, that's a sign. We're still at about double. I checked the last couple of weeks. We're maybe double the background rate of earthquakes out there. And it hasn't quite died off. So there's a potential, certainly, that that's an indication that something's still restless. Some stress hasn't been relieved yet, but only time will tell. So there's a few of the things that have happened in the last year. 4 very, very different earthquakes. Very different places, very different causes, different magnitudes, different felt reports. None of them damaging. But I want to look at the magnitude part of that, because the magnitude part is a little unsatisfying. The significance of these earthquakes didn't scale by magnitude. The magnitude 7.9 earthquake really, much as it seems weird, really didn't do much at all as far as impacting people. So somehow magnitude isn't capturing what we really want. We want something else, something beyond magnitude. And we're going to come back and hit on that for a while. First thing I want to do is just I want to talk a little bit about our organization and where all this information comes from. Maybe a little bit of ego in this, but I'm very proud of what we do, and I always take an opportunity to share with people where that comes from, because earthquake information we treat a little bit like the weather. You turn on the radio in the morning, you hear about what happened last night, 4 o'clock in the morning, magnitude 6 point whatever. Well, that comes from somewhere. So quickly, I'll step through a few slides that give you some flavor for what that process is and how we get there. So I'll start by highlighting people. As with all endeavors like this, there are real human beings behind this activity. These are the faces of the Alaska Earthquake Center. A wide range of disciplines, from technical skills in keeping field equipment running, to data analysis, to outreach and education. A lot of different things that come together to make the center run. Most of you probably know this, because I think a decent fraction of you in the room actually work here. This is the Geophysical Institute. We are housed at the GI in the LV building, and it is open. People do come through. People are welcome at times. There are opportunities for tours. However, to be really honest, if you want to be part of a discussion about earthquakes, if you've got questions, if you want to talk to people, the best place really is, I hate to say it, it's probably our Facebook page. I don't care if you go there and click the little like button or whatever. I don't know if there is one. What I care about is it's probably the most vibrant discussion of earthquakes in Alaska that's going on right now. So it's always there, and it's been a great resource, a good opportunity for people to throw around questions that don't get answered here, for example. Here's the seismic network. This is a map of the stations that record. These are earthquake monitoring stations around the state. They are operated by the center as well as partner organizations like the Volcano Observatory and other groups that we work with. And all of that data we use to track activity around the state. In our urban centers, Fairbanks, Anchorage, we've got much denser equipment to try and provide a little more connection with the built environment. But this is really the backbone of what we do. Data from all of these sensors comes into the center in real time. Here's what an earthquake might look like. This is actually the big Rat Islands earthquake. Each one of these lines is 1 seismogram. It's about 20 minutes worth of data. And what we're looking at is stations that were really close to the earthquake out in the Aleutians. Earthquake shows up there, and over the next 5 minutes, we watch it kind of ripple out to all the other stations. And so using that kind of information, using the timing, the relative timing of arrivals, is how we track, how we figure out where earthquakes occur. I'm going to show, that's right, I got a little video over here kind of to show that process. Strange icon there. We're going to take a look. This is the Squentna earthquake, so the earthquake north of Anchorage back in September. And what we see is a little circle, a little colored circle at each seismic station. And the color of that circle represents the ground motion. So what we're going to see when the earthquake starts is we are going to see that motion ripple out. It'll start there, and it'll take time to get to the other stations. This is sped up about 20 times faster, roughly, than real life. So it'll go kind of quick. But here comes the earthquake, and there it goes. So you can see it starts in the middle and it radiates out. Takes a little while to get out to the Alaska Peninsula, finally out there and all the way up north. And then eventually it begins to fade away. And now this is just chatter. This is just the seismic waves, the energy bouncing all around the place after, in the minutes after the earthquake. I was going to go back to that. I'm just going to step through this. Let's see. There we go. I kind of like to do this back and forth, back and forth. You can kind of see that it ripples out, starts in the middle. Really simple. I know everyone probably thinks about it. It's not that different than a ripple in a pond, but that motion is exactly what's used to pinpoint where earthquake comes from. So all that information goes out through all sorts of different mechanisms now. I think there's a new phone app every day or every week that's willing to notify me when there's an earthquake in Alaska, because data goes all over the place. But if it's something from Alaska, ultimately all of this data traces back to what goes on at the earthquake center. It just goes out through many, many, many different mechanisms. So one of our emphases is the here and now. The most important earthquake is usually the one that happened 2 minutes ago. So a lot of our efforts go into that 24/7 sort of response. But in addition, we track what's happened over the past many, many years. We keep that record. The old adage that history repeats itself turns out to be one of our more powerful tools in figuring out or anticipating what to expect in the future, looking at the something near 500,000 now, I believe, earthquakes in the catalog, we call it, the historical catalog. They give us a lot of clues, not all the clues, but a lot of clues about what to expect in the future. So, onward, here we go. I want to go back to this question, though, of how, well, the shortcomings of magnitude and what we really care about. Because I think what actually impacts people, what impacts buildings, what impacts communities, not the magnitude of an earthquake, but the shaking itself. So I'll illustrate that. This is data recorded in several places around Fairbanks during the August 30th Minto earthquake. And what you see is a lot of variety. These are about 25 seconds long. Different kinds of signals in each place. Clearly, there's a ton of information in there, but that's kind of a mouthful to carry around. It's hard to explain that to someone. We're looking for ways to distill that to simple numbers, something the equivalent of like a magnitude scale or something that we could say, oh, well, it shook as blank here, but blank there, and talk about these differences, because if you're building in Esther versus on Chena Ridge, you might want to understand that, those earthquakes are really felt quite differently in those two places. So I'm going to back up. I'm going to step aside here for a minute, talk about how we measure motion. And this is my coffee cup on the dashboard of the car, filled with steaming hot coffee. I'm going to bet, I'll make a challenge here, but I think I can drive 60 miles an hour down the Mitchell Expressway without spilling that coffee. Kids, don't try that at home, but as long as the car's cruising down the highway, no problem. Coffee's just fine in there. When do we run into problems? When you stop, that's right. The moment you touch the brakes, everything changes. All bets are off then, right? Or accelerating out of a stoplight or something changes. Accelerations are what cause me problems with a coffee cup on the dashboard. I saw some people walking in here with notebooks. Anyone taking this, getting credit from their teachers at school? Awesome. Okay, if you want to impress them, right? So this is Newton's second law in action here. It basically states the force on an object is proportional to its accelerations. Acceleration basically equals force. These two things are inseparable. So when we accelerate in the car, slam on the brakes, or accelerate out of a stoplight, we're applying a force to this coffee cup. I know you're wondering where he's going with this. This is really no different. Coffee cup on the dashboard is no different than a building sitting in the middle of town. The car applies forces to the coffee cup. The earthquake applies forces to the buildings. All we need now is some scale, some way to talk about that. But we understand, all of us have a pretty good intuitive understanding of acceleration. We've talked, as long as we've been alive, about g-forces. Ooh, there were a lot of g-forces in that turn. Wikipedia tells me that modern roller coasters, this actually really surprised me if the author who edited Wikipedia is to be believed, that a lot of modern roller coasters produce 4 to 6 g, that is 4 to 6 times the acceleration of gravity. That was way more than I would have estimated. But that's an up and down acceleration. In the car, it's going to be more side to side. If I come to a stop, if I'm driving down the road and come to a stop reasonably promptly, it's probably about a 1/4 g. Moose steps out in the road and I stop very, very suddenly, not screeching to a halt, but awkwardly fast. That might be 1/2 g. So we're going to call that, we're going to refer to that as 50% of g, 50% of gravity. So we all know what 50% of g is. That is slamming on the brakes in your car. So we've got a unit for acceleration now. So we're going to go back to our seismograms here. These are actually records of acceleration. The scale is a little bit small. I've got it down here, but that's plus or minus 1% of g. So during this earthquake, the Esther Fire Station, which is where this seismic station is located, had experienced about 3% of g. So accelerations on that level. That's not that impressive. 3% doesn't seem that big. But remember, it's going one direction, then the other direction. So you kind of flopping your head one side, and then accelerating to the other, back, forth, accelerating. So this would be more like hitting your brakes on and off, on and off, on and off as you're going down the highway. So actually fairly significant motion. Station up on Sheena Ridge, a little bit less than 1% g. So now we've got numbers that we can use to talk about how that earthquake actually impacted us. My great hope is that someday people will be demanding of what their acceleration is, or we refer to this as peak ground acceleration, at times for short, or PGA. My great hope is that should be careful about this, but my hope is that people will call up after an earthquake, they will hassle us, hound us by email, on the phone, and say, yeah, I know what the magnitude is, but I was on 2nd and Cushman, and I want to know what my acceleration was. What was my acceleration? Because that is a much more meaningful measure. By the way, there are tools. We do publish that information for relevant earthquakes for the motivated listener in the audience. So back to my building. What does that mean then? What can we do with these accelerations? Well, from a design perspective, I just happen to be picking on my building, but that's because the GI's got some interesting things going on. It's an older building. Fair amount of concrete. It's been retrofit multiple times for one thing or another. It's got some other buildings hanging on it now. There's this antenna sitting up on top. A lot of things you might want to think about if you were addressing how will it respond in an earthquake. A moment ago, we talked about how accelerations and forces were inseparable. They were essentially two sides of the same coin. Earthquake or building design, engineering, is all about forces. You're building a taller building, well, what kind of supports do you need to hold that load? What do you need to deal with the snow load? What do you need to deal with the wind load? It's all about forces. So all we need to do, really, is specify an acceptable acceleration. Do we want to build a building that can handle 2% G? Building that can handle 8% G, 20% G, 50% G? Once we pick that number, then the engineering takes over. It's going to cost more, of course. We may not want to do that, but we can do it once we know. So from a design perspective, accelerations are really, really important. These are the foundations of our building codes. Oh yes, a schematic of the floor just to motivate the notion that these are structural choices we can make in our buildings. That's all great, if we know what kind of acceleration to anticipate. So enter the seismic hazard map. This is a map of seismic hazard. The scale is a little bit hard to see over there, and it gets a little wonky, but I'll walk you through it real quickly. This seismic hazard is given as a maximum, or as a likely acceleration, this peak ground acceleration we're talking about, in a given amount of time. It's all probabilistic. So we talk about here something that has a 2% chance of happening in 50 years. I'll translate that. For me, that means, not probable, but certainly possible. So what is the not probable, but certainly possible acceleration that we might experience? The blues here are in the 2, 4, 8% G range. Okay, these are numbers that we've worked with now a few times. That starts to make sense to us. The yellows, we're talking 20, 30, 40% G. That was slamming on the car brakes really hard, right? And down in the red and the dark oranges, we're up at around 100% G. At 100% G, if it's vertical at least, that's accelerations at which you can get airborne. So that's pretty strong. But that's how seismic hazard is given. And again, this isn't some sort of abstract research endeavor. This has real on-the-ground implications for how we prepare and what we do. So this map is actually written into the building codes, into the international building codes. It's revised every few years. It's a rather dull read, I would say, but I've leafed through it at least. Many pages devoted to earthquake loads, hazards, but it is premised on this very notion. So other groups that care about the potential accelerations in point A or point B, well, the insurance industry. Think about what a business that is to be in. Think about being in the business of earthquake insurance. You're going to collect policies from thousands and thousands of people. You better have some good economics to back up your business model. I guarantee you that earthquake insurance policies that are being written in Alaska are very, very cognizant of this, if not tied exactly to this map here. That I don't know. They may do some custom things. But this is exactly what they're doing to set rates. You know, the rates in the blue and yellow areas are not the same as the rates in the orange and red areas. Just a small aside, earthquake insurance is a pretty complicated endeavor. I can't stand here and say that's an absolute must or don't touch it. There's a nice brochure out in the entrance if anyone's ever wondered about earthquake insurance. But again, it's not the most thrilling read. But I brought that, and it does walk through some of the technical aspects for people who are thinking about it. Looks like that. It's out on the table. So, all right. Let's think about what else we can do with this seismic hazard, this map of where our hazards are higher, where they're lower. Here's one example. We can use it to interact. We can lay over it our developed things, the things that we actually build as a society. In this case, schools. We care about schools. Everybody cares about schools. Long ago identified that schools pose particular challenges for earthquake hazards because they're concentrators of people. You get a lot of people in one place. It doesn't help that they're kids, and we tend to treat kids well. So we've got schools, we've got places that we care about. Now we can overlay that on the map of the seismic hazard. We got two different pieces in there. We can begin to make educated decisions or guesses or about, say, where we put priorities or where we put funding or where we don't have to worry about those things. So this is a map produced a couple years ago by the Seismic Hazard Safety Commission. The blue dots are schools where it is considered possible or more than a little possible in the course of a 50-year period to have shaking of 10% G. If you were going to make a decision, you might say, well, you know, let's pay a little closer attention to the blue schools than the ones in black. This is a tool for making educated decisions about where we put resources and where we don't. So the key thing on this map, we got two different kinds of data. One of them is a hazard. One of them is inherent in the Earth itself. those shaded colors, there's nothing we are going to do as humans to change the fact that there's a really high seismic hazard in this area, and it doesn't quite seem to be as strong over there. Now, there's all sorts of mistakes in this. There's problems. This is only as good as the knowledge we have. But based on the knowledge we have today, that's something we can't change. The part that we have control over is what's built on top of it. That's where we make decisions day in and day out about our priorities as a society. So we're going to do a little math here. Anybody here had class in partial differential equations? What about pre-calc? All right, who's had multiplication? Sweet. Come on, Carl. You can raise your hand too. Okay, we're all on the same page then. We're going to do a little multiplication. I joke, and this is a really simple thing to write down, but actually there's a lot of weight to it. This is actually a very meaningful expression here. When we take hazard, that is the term that describes the part of this system that is beyond our control, the part that is the Earth itself. The vulnerability, that's the built stuff. That's the choices we've made. This is the classic Three Little Pigs. Did you build your house out of, what was it, sticks? Straw, sticks, and brick, was that right? Neither really great. None of them great for earthquakes, by the way. A wood-framed house would have been better, but that's okay. That's the vulnerability part. And what we actually care about most of the time is this risk. It's in many formulations, it really is the multiplication of these two things. But philosophically, it's kind of important for us to keep things in these two different bins, the hazard stuff and the vulnerability stuff, recognizing that it's actually kind of the combination of the two that we care about. I always think about that old saying, if a tree falls in the forest, and how's that go? A tree falls in the forest and nobody's there, does it make a noise? And that's way too deep for me to figure out. But what I do know is that if a tree falls in the woods and there's nobody there, then nobody's going to get hurt. And if a tree falls in a forest really crowded with people, someone's likely to get hurt. So that's kind of the same, there's the tree, and there's the presence or absence of people in the forest. So let's walk through just a couple of examples, a couple of recent global earthquakes, and take a look through this lens of sort of hazard and vulnerability. This is a picture from Christchurch, New Zealand, just shy of 4 years ago now. Magnitude 6.3 earthquake that was just devastating and came as a considerable surprise. There's a cautionary note in here in that magnitude 6.3 earthquakes are not uncommon at all around us. Heck, that's what the Squentna earthquake was this year. Didn't do nearly this damage for lots of reasons, but we should take it in Alaska as a cautionary note not to undervalue that magnitude scale. 6 is a big, big earthquake. Anyway, not that common, not a common event in Christchurch at all. Many, they had not seen an earthquake like this in recorded times. They certainly have distant earthquakes in New Zealand, but not here. And so the vulnerability in Christchurch was actually pretty high for a first world country. The hazard turned out to be much stronger than they anticipated, and as a result, 158, give or take, people lost their lives. And really part of what was so devastating about this is it kind of came out of the blue. It was a surprise earthquake. Just for perspective, the peak ground accelerations, this idea of acceleration we've been talking about, 200% G measured in Christchurch. So twice the acceleration of gravity. Magnitude 6.3. Keep that in the back of your head. There was the earthquake in Japan, of course, by far the biggest singular event. I still get a lump in my throat when I look at this figure, or look at this picture. It's just a haunting moment in time. And one of the many, many tragedies in this earthquake is that Japan did their homework. Japan has invested more energy more resources into earthquake understanding and preparedness than anywhere else in the world. They are, and long have been, the role model. So there's something grossly unfair. Not that this earthquake would ever be fair, but there's something notably unfair in this particular case. So their vulnerability, they're vulnerable because it's a dense urban society with a lot of people and a lot of development, but they had done everything they could to bring down the vulnerability side of that equation. What caught them is that this earthquake was not expected. This was an earthquake that wasn't really thought to be a possibility. And so that hazard side was so big that it just overwhelmed the preparations that they had done and the things they did have in place. I've heard many times now that, well, the tsunami breached the tsunami barricade. There's actually, underneath this wall of water here, is the berms built in place specifically to hold back tsunamis. And well, the berms weren't high enough. I'm hard-pressed to think of other places in the world where they've even built such a thing. So again, there's something notably scientifically unjust about this earthquake. But we can take it all back to that hazards, vulnerability, risk equation. I think the take-home point of this, what I'm trying to get at, and I guess what's really at the root of what we do in earthquake monitoring and preparedness as a state is, forgive the cheesy clip art, but this is a good comparison. Whether we think about earthquakes as random acts of God, that is, I don't know what it is, I know it could hit someday, it's going to come out of left field, see what happens, or more in the category of rare, but there are things we can do to influence our odds. There are things we can do to understand the probabilities of certain things. I know if I'm rolling dice, 2 dice, I got a far better chance of rolling a 7 than a 2. Think about that, Ezra, you figured it out. Same thing with earthquakes. There are certain scenarios that are far more likely, certain places where maybe we should be putting time, attention, resources, and other things that frankly maybe we don't need to worry about, or in certain times and places. So that's kind of a through-going theme here, and that's where, just to hit on it once again, we get back to this notion of making hard decisions and figuring out where we put resources. It's not an easy time nationally, state-wise. It's not like there's all the money in the world. It's easy to say, well, let's just build everything to unbelievably high standards. It doesn't work that way. We have to make real choices. And a big part of this, a big part of why we try to understand risk is to figure out what we can do that's cost-effective to lower vulnerabilities, and really to think about what we don't have to worry about. That's actually a money saver. So I'll get off that topic, but this was sort of the theme that ran through those slides. All right, I want to hit on just a couple of examples, a couple of little hazards and a couple more vulnerability examples, and then I'll get toward wrapping up. But here's a map, a couple of random, they come from different areas. Just sort of broaden our thinking on this. This is a map of Anchorage. This is a map of soil susceptibilities. Basically, green areas have soils that are considered very stable in earthquakes. Light green, yellow, not so much, and reds and oranges, all bets are off when shaking begins. And this isn't perfect. You can go down and you can squabble with little pieces here and there. However, this gives us some foundation for better understanding the hazard side of this equation in an area like Anchorage. Most of Alaska hasn't had this type of investigation, but Anchorage has been very proactive with 1964 in their history. Anchorage has actually been, for many years, were considered leaders in the area of building codes and good development. So this is a kind of tool that bolsters our understanding of the hazards part of that equation. Think back for just a moment to the slide. I'm not going to show it, but the slide with Fairbanks and the different levels of shaking during the Minto earthquake. I still think about that one. Chena Ridge, Esther, not far apart. There's a big difference between the two. Chena Ridge is up on a bedrock hill, and Esther, at least the fire station, is not. And surely we are seeing these kinds of differences between those two areas. But that's where this kind of information becomes significant, becomes useful. I'm going to show another piece. This is out of just a little snippet of text that I cut out of a forthcoming report that the Matsu Borough undertook on their schools. So this is an engineering analysis of different school facilities and looking at well, basically their earthquake susceptibility. So now we're on the vulnerability side. This is the built infrastructure. Since it's draft, I replace school names with school A, B, C, and D. They're kind of irrelevant to the discussion. But the important points here is you can go through, take a look at the way they're built, a quick look at engineering plans, and do some things and come up with rough estimates. These are not perfect, but ideas about, well, just how earthquake robust is this structure or not. And the key thing is using standard FEMA guidelines. These come through. This one, School A, has a collapse risk of 3%, 1.3%, 3%. Here's one at 50%. A particular structure was identified that, for various historic reasons, is not considered nearly as strong as the others. Well, you got a little bit of funding. Where do you put it? This is the kind of information that helps make those decisions. So this is a good example of what we can do at sort of the vulnerability side. Yeah, I singled that out. Precast and masonry construction, those are always things that cause concerns for us. So this is great. This is one way of looking at individual structures and buildings. And to be fair, the construction community, the building community has long been dealing with these things, perhaps not perfectly, but it's been pretty proactive, if not proactive, at least legally required and bound to address some of these things, at least in public buildings. One of the areas that I think we can grow is looking at this on a community-wide level. We do not do many things, at least in this state, where we consider the impacts of an earthquake from a community perspective. We think about, the shelves in the in the bedroom, make sure those don't fall over. Okay, put some bolts in, fine. We think about the health of a particular building, but we do very few exercises dealing with the larger response as a community. I'll just point out, there is a forthcoming, or a guide that just came out this fall, specific to Alaska on how to perform such community-level kinds of exercises. And it's a long-winded thing. We put a lot of text in it with a lot of different steps and guidelines, but it can really be boiled down to exactly what we've been talking about all along. Identify your hazards. If you don't know your vulnerabilities, go out and actually catalog them and calculate your risk. Then you know what to do, and you can figure out either how to mitigate them or at least how to deal with them when you're done. An example, I'll give a local example. In that opening slide, the title slide had that fracture on the Richardson Highway in 1937. This is what we think, very roughly, the shaking from that earthquake was. So red areas and orange are very strong shaking, and then as you get out into the yellow areas, shaking was lesser. And we think this is very approximately where the fault was in 1937. From a Fairbanks perspective, the important thing is that this is east of town. Okay, we got two main supply roads in and out of town, right? We got the road to the east, Richardson. We got the road to the west, the parks. These are our two arteries. Also our telecommunications arteries. That's where our fibers run. It's also, we've got the railroad on the western side. This is the east side of town scenario, if you will. if you're planning as Fairbanks, if you're thinking about this earthquake, well, things to keep in mind. Let's see, Eielson, likely to be hit. Probably not looking to Eielson for assistance during that earthquake. Possible disruptions of anything that's headed out in this direction, but probably pretty fine on the west side of town. Probably unlikely to mess with the railroad. Okay, the same earthquake is also considered to be, is actually fairly likely in the Minto region, or is a possibility. Magnitude 7 to 7.5 is considered a reasonable possibility in the Minto region someday. That'll be the same earthquake, but on the other side of town. In that scenario, I'm going to watch out for the railroad. I'm not sure I want to be relying on that, but the Richardson Highway is probably open. So 2 different scenarios that get kind of highlight the way we plan around specific kinds of events. One last example here. I'll pull from Valdez. This is a new study, just came out recently, looking at the tsunami, the actual tsunami, likely tsunami impacts in Valdez. And again, the scale is small, but to translate, the yellows are tsunami or water depths of on the order of 15 feet or so, tapering off to maybe 3 to 5 feet in the blue areas. This is kind of a worst case, if you will, a maximum likelihood or a maximum inundation scenario for tsunamis in Valdez. And this is great. You can use this. You can begin to plan. You can make some decisions about what's smart to do here versus what's smart to do in other places. This is the hazard side. We haven't taken people into account too much. But what we could do is say, well, how much time does it take to evacuate out of different areas on here? So this is a figure of evacuation time. The blues mean 10 to 20 minutes maybe, and the yellows and oranges are saying half an hour or more for a person on foot to walk out of those areas. That would be great if it was all a giant parking lot, but you can't just walk from point A to point B. We walk on roads. So you can go another layer, add in the road system, and you can calculate, you can begin to estimate the evacuation times from particular places in and around town. If your tsunami scenario allows 10 minutes, you can figure out safe zones and unsafe zones. There's another slide that I'm not going to put up, but you could take this one step further and overlay where population is on a work day or on a weekend or in the summer and on the winter. And this gets kind of controversial, but you can start to put estimated deaths on this figure. And that's uncomfortable, and there's a lot of things that are complicated about that. But that's where this begins to take on meaning, and that's exactly the exercise that should be done. So I guess I did have one final example. This is actually Kodiak. Kodiak has been very forward-thinking about their earthquake preparations in recent years. And this is a study conducted with FEMA where a particular earthquake scenario was assembled, one of the likely earthquakes or one of the anticipated earthquakes in the Kodiak area, and then going through and doing that building by building analysis and quickly get some sense for the types of construction. And what you're looking at here for that particular earthquake is estimated losses. Orange circles are $1 million or more to that particular structure. And you, as a community, you begin to get a sense for what state are we in following an earthquake. Where are our issues? Where are our assets at that time? And likewise, there is a comparable estimated population loss figure for this too that I haven't put up. So these are great examples, I think, of where we can go beyond this kind of random act of God way of thinking about earthquakes and begin to do things that change the probabilities, or at a bare minimum understand the probabilities and allow us to make good decisions. So where do we stand as a state? Last slide. I think we're doing an okay job on the hazards, the broad brush hazards side. The kinds of information that give us sort of a sweeping view, comparisons of this area of the state or that area of the state. Yeah, there's always work to be done, many improvements, and I can point out shortcomings, but we're not too bad about this. Where I think we get a little bit weaker is in actually connecting this to communities, making this relevant at the scale of individual villages, even down to the building and neighborhood level. On the vulnerability side, well, there's the personal side. There will always be the individual and their house level. That's just an ongoing education and outreach exercise, I suppose. At the building level, the engineering and construction communities, while not perfect, where building codes are enforced in this state, I think we're in okay shape. The one I'm probably the most concerned about is the large-scale infrastructure. We have so many things in 2015 that connect us, so many big things, be they pipelines, mines, telecommunications, transportation, so many systems that keep all the parts of what we do functioning and connected. We don't put much energy, we don't put enough, in my opinion, energy into assessing the earthquake robustness and the earthquake risks and the vulnerabilities associated with those things. We have done some things that are good examples of what's possible, but these are really the kinds of studies that I think we are well poised to be doing more of, and I would encourage all communities in the state to think increasingly about it from this perspective. So I've talked plenty. Thank you very much for your attention, and happy to take questions.